I've been teaching in the engineering and medical statistics community for about 5-6 years, almost every semester for that entire period. And I've also taught programming classes, and my background is eclectic and involves a lot of methods. And that's really why I gravitated towards JMP for a lot of my analysis work, and especially for teaching, because I taught programming, but if I don't have to teach programming, I can focus more on methodology and theory. JMP is a interactive GUI-based statistics software package from SAS. It's currently on version 14. I think version 14 came out last year. It's interactive, it's visual, it's easy to use. However, there's a lot of methods and techniques in there, so that's where books like mine come into place, because by the variety of methods, it can become slightly less easy to use just because of the plethora of options. But there's no coding required, which as a research scientist sometimes seems like a limitation, but there's coding available in JMP scripting language, and it also interfaces with just about every method and common software package, Excel, SAS. Of course, it interfaces with SAS, R, MATLAB, Python. So if you do code in those languages, you can leverage the power where needed. And we even had one student once who did a thesis where they used JMP for some methods where JMP was perfectly designed for, and then MATLAB for a few other methods where it was more esoteric, theoretical, neural network based, and so the portability is very good. Excel also you can get a built-in JMP package that gives you an extra toolbar add-in, but we won't be going down that path today. So why teach with JMP? It's really the genesis of my book. I saw both in engineering books and medical statistics books that there's a major limitation in that the books focus on theory, and they might show analysis results, especially on more advanced methods, but they don't show you how to generate those methods. And if your class is full of medical students or medical researchers, or if you've worked with medical researchers, you know that medical researchers do experiments throughout the year, and then at the end of those experiments only come back to the computers. On the engineering side, we're used to people using computers daily, and so the coding knowledge doesn't go away and the software knowledge doesn't go away, but in the medical and biomedical world, the knowledge can go away fast. And throughout this, I was consulting with a research lab, and they were very unhappy with their software, and they said, well, yeah, you showed me very nicely how you can do this in JMP. I wish I could have a book that would walk me through all the steps. And a few years later, here comes my textbook. So there's some basics on JMP, and this doesn't encompass everything, but it largely encompasses what I want to talk about, and most statistical data analysis, because I want to dig into playing with JMP and not talking about through a JMP journal. There's some basics in becoming familiar with JMP, sample data, getting data into JMP, because you're not going to be playing with the built-in data sets. You'll be wanting to put your own data into JMP, and how do I set up a data table, etc. So JMP can analyze it effectively. A big challenge that I've found is not the analysis, it's how do I wrangle the data so that it is in the right format and structure that software will want to appropriately handle it. Data visualization, and which can show you some insight initially into data, and then modeling, and I use the term modeling very broadly to encompass any mathematical model from a confidence interval up to a highly complicated neural network or learning approach, and then analysis and interpretation, because unless things in my research world turn out, humans still needs to interpret and analyze the data. Let's start with some built-in data. So we see we have a JMP window here, and this, when you open up JMP, it'll show you something like this. It'll show you the recent files. So this is the files that I will largely be talking about today. And it says a window list, and the window list shows what is open in JMP at the moment, and the only thing I have open is my Biostatistics JMP journal. We have some typical tables and drop-down menus at the top. To get started, we can find some sample data, and JMP has a lot of sample data. And Windows 10, close all my windows again. So they are grouped by approaches, analysis methods. So this is someone that fast stops that a certain data type fits a certain method. So if we click on regression, we can see that Anscombe data or body fat, these are appropriate methods for regression. We can also open a sample data directory or see an alphabetical list of all sample data files. These two kind of go hand in hand, because you really need to know the name of the data file in both places. So we'll do an alphabetical list, and here's 300 or 400 or so built-in sample data sets. Some of them even come along with the approaches that might fit into place. I'm going to load one that we'll see a little later. I have to find it. It's called Iris. So this is the famous Fisher Iris data set. We have 4 measurements: sepal length, sepal width, petal length, and then the species of the iris, and there are 50 observations per species. We'll revisit this later. It's a relatively famous data set, and we'll move on to the next part of what do we do if we don't have this. So I have a example data set. This is actually a data from my book that is fabricated based on a study of BDNF alleles and mutant wild type differentiations. And typically we might collect data where we have columns where we put in the mutant type and then the wild type. Now we have to learn what does the software want to see when we analyze it. So let's go through and open up this file. And I want my desktop. I want my webinar. And I will open up the BDNF. And what we'll see is that JMP gives me a preview of what's in the file. Now I can go and enforce the first row as labels. Be careful. You can say best guess, but sometimes that works out, sometimes it doesn't. If you choose wrong, you might have all categorical terms when you really have a nominal or continuous data. But in this case, we'll say best guess and hit OK. And JMP will let me import data in Excel through its wizard, and I have a lot of options here, and I don't need to mess with at the moment because this is a very simple problem, but in more complex ones, you can go in and tell what columns headers start on what rows. I can hit next to see more options. So it says data preview. It does have replicate data spanning rows, and I can really customize this for very complicated data problems. There's nothing too complicated here, though. So now I have my data set loaded into JMP. But there's one minor problem. If I want to do a t-test on this data set, or great confidence intervals, or do an analysis of variance, I have 2 columns that are treated as separate independent variables. And that's where you really need to know the assumptions of the software, because software is is stupid. It just has rules and no mercy. But if you know what the rules are, you can take full advantage of the power. So we know we have a problem here where we want the data all in one column. That's our output, and another column that relates to what category are we in. Let's also look around and see what we have in our data table. We have columns. JMP's identifying this as continuous. So if I click on here, I can change it to, I don't want to in this case, to another data type, to ordinal or nominal. I can also investigate a lot of other properties that way. So if I have something that's loaded incorrectly with a few tricks, I can easily change that by changing the type of data. Well, what we want to do is reorganize the data. The table menu gives me a lot of options here. The option we really want in this case is stack. I want to stack these columns on top of each other. But well, we can see there's a lot of other possible options if we wanted them. I'll click on stack. I'm going to select both of these columns and select stack columns. And there's a variety of other options here that we can look at. Stack by row. If I unclick this, and it'll stack it directly. If I keep it clicked, it'll be interleaved. So I'm going to hit stack by row. I'm going to click keep the dialog box open just so we can see what happens. So I hit OK. And we'll see it create a new data table called Untitled 30. So that's the 30th data table I've opened since I've opened up JMP this morning. I unclick stack by row. They'll need a dialog box again, so I unclick keep dialog box open. So this is a nice feature. So if you want to try things, you can keep the dialog box open, so you don't have to keep finding the course of action you had in the menu. Hit OK. So you have the same data here, just organized slightly differently. Depending on your preference, one may or may not be preferable, but it's the same number, so that's a nice little trick we can examine. I can go and now that I have the data in a format that JMP is ready for, I can go and plot it. So one thing we can do next is visualize the data. So I'll open up this part of the JMP journal, and we'll look at Graph Builder. JMP has a lot of graph options. Some are extremely useful on almost every data set. Some are very specific to certain problems. Graph Builder is one of the most powerful tools because it lets me do almost everything in the other options with some limitations. So I'm going to go drag, open up Graph Builder, and I have a general box where I have these options. I have Y, I have X, and I have a general hint I want to drag the variable into the drop zone. So if I grab my data variable, as soon as I start moving, it highlights all the possible drop zones. Now some of these won't be very helpful to us, but if I drag data over to the Y-axis, I can now see the dynamic range of the data. If I grab labels and move this to X, I now see that I have the data separated by the two types. If I look at the top, I see a bunch of plotting options. So I have points currently. If I click on the bars, I can create a bar chart. I can also go and say, maybe I want an error bar. So if I click over here on the left, I find error bars. I can show standard error. I can show a 95% confidence interval. I don't say at the bottom that it's 95% confidence interval, but that's just the built-in default. And we can see, in general, how different are these two groups. Once I'm satisfied with the chart, I can hit Done. And this is a chart that's just about ready to be displayed. If I want to do any other options with this, I can see this little blue thin bar at the top. If I click on that, it shows me a lot of options, including saving. If I want to just paste this into a figure, I can I can right-click on it, hit Edit, copy graph, and then I can paste that into whatever format I want. So we had an initial guess showing that the two types were different. We probably want to do a little bit of analysis of this. So we create a simple confidence interval, but we can also go and examine further. So if I go to Analyze, fit y by x or fit model, these two are the more encompassing options we have. Fit y by x lets me fit one dependent and one independent variable, but if I have more independent variables, then I want to use fit model, but both will give me the same result, just a slightly different relation. Fit y by x is a nice place to start. It asks me for my response, and it says it's required. So it's not going to run anything until it tells me what to do. I put the data in there. Now it asks me for what factor. I'm doing a typical ANOVA t-test type of approach. My factor can be a category in this case. And it has a quadrant here of the available options. The second label went in. You might have noticed that one way appeared up above. If I delete label, it goes away. The quadrant is saying based on your y and your x, what statistical approach will be applied. And we can see categorical x and a continuous y is a one-way analysis. It can also give us if I have more than 3 parameters, it will give me a typical one-way ANOVA. If I have 2 parameter categories, it'll do a t-test ANOVA approach. If I had a continuous x and continuous y, it will give me a bivariate fit or simple linear regression model. Continuous x and a categorical y, I can get a logistic regression model. If I had everything as categorical, I can do a contingency table. There's options for blocking. So there is a nice added ability that I can do essentially 2 x's if I really want to view of blocking it that way, but I can add a blocking term. We have a weighting term for our variables. We can add that. Frequency or by our extra abilities. We'll see the power of frequency in a minute. But this is really useful if I have something that's more tabulated and not as columns of data. By will say I might have another factor that says this is the male group, this is the female group, and by would really just repeat the analysis for both groups. So I'd have 2 sets of statistical models to interpret. I'll hit OK. Nothing appears right away except the plot that we've already seen before, but if I hit this little red triangle, which the little red triangle is key and jump, it's where we find a lot of our functionality. I can see the option for a mean ANOVA pooled t-test. I can see a general t-test. So this is the more conservative assumption. And I want to go down the analysis of variance space, so we'll click on that one. This is the assumption assuming equal variances. It will give me a summary fit table, which includes R squared, adjusted R squared, and basic summary values. It will add a bounding box around where the mean of the data and where the distribution generally is. And we'll see the pool t-test has the p-values for the two-sided and the one-sided cases. And I can also see the analysis of variance version and the means for the analysis of variance. So even though it looks like a different group, we saw when we flashed up the 95% confidence interval, statistically there might not be a difference in these two groupings here. The p-value from the ANOVA table, remember the null is that for the simple case is that there essentially is no difference between the groups. We've seen the pooled t-test, it's the same thing. You have the exact same p-value. There's a nice theorem called Cochran's theorem that links back and says for the simple one parameter, one x, one y case, the t ratio is equivalent to the f ratio. Now, it doesn't hold if we have multiple x's, but that's a nice equivalence we can see here. And so we can do it, very simple analysis here. So let's close out of this. We'll close out using wild type data. But what we want to do is let's look at another data set I have called U.S. opioid overdose data. And so this is a data set from my book that I collected using the real world U.S. state opioid overdose rate and numbers for the year 2013-14. And we can do some interesting analysis, visual analysis here. And JMP has a very nice ability that would take me a lot of coding in R or MATLAB to replace. So I'm going to return to Graph Builder, and I'm going to select state. And notice state is in the typical two-letter U.S. state abbreviation. So I'm going to drag that into the middle. Apparently, California is highlighted. If we look at the table, California is a row that I've selected in the table, so I'm just going to click in the white space here to unselect that. And now I'm going to drag over one of these numbers. We'll start with 2013, the number, and I'm going to drag that to color. And this is a good basic epidemiology result. So we see that California had the highest number of opioid overdoses in 2013. Let's drag the 2014 number over. California is still number one, but we see Ohio, Pennsylvania, Florida have increased a little bit. But what if we go back and look at the rate? So 2013 rate instead of the raw count, and now we see that California is not even near the top. West Virginia is near the top. West Virginia, Kentucky, New Mexico, Utah, and then Ohio, Nevada, Rhode Island apparently are more prominent than that. We can go and look at the rate for 2014. Hasn't changed too much, except the rate for New Mexico has increased, and Ohio seems to have increased as well. And we dug into, in my book, is digging down into an example of Ohio counties. Since I live in Ohio, it's more relevant to me, and since the number one pill prescriber was in my hometown, it hits home a lot. But there's more nuances I want to dig further into Ohio counties or certain counties. The JMP has a lot of capabilities here that are very nice and built in. I can hit done, and we have a decent graphic. And I think somewhere on the internet I created one that spans about 10-year period, just taking screenshots and building an animated GIF. But this is a good example of basic epidemiology work. We have to look at rates because California has maybe 30 times more population than West Virginia, but per 100,000 people, West Virginia has a much higher rate. That's why it's in the news on the opioid epidemic in the Rust Belt. It takes my students a little bit of time to see this, but eventually they see an example like this, and it starts to click that okay, rate starts to make sense. So I'm going to go next, and let's go to Fisher-Iris. So Fisher-Iris has a few other nice abilities. So I open up the built-in Fisher-Iris, and it has these ready-made functions at the left. So if I went and saved, so let's go back to my Ohio opioid data set. I'm going to just reproduce the analysis really fast. I'll put state, 2014 rate. I'll hit done. I'm going to hit the red triangle. I'm going to save script to data table. And I can name this as states colored by 2014 rate. I'll hit OK. And when I look at my data table, I have an option to reproduce the analysis. So if I hit close, I can hit this little green triangle and reproduce what we just saw. So let's go back to Fisher Iris, and Fisher Iris comes with a lot of these pre-populated approaches. I have a nominal logistic model, so if I hit run, I can see what Ash thinks is the best or a representative logistic regression approach for Fisher Iris. A nice approach is coming from the Department of Defense community is what we care about usually is confusion matrices and receiver operating characteristics curves. So I have that option here. I can look at a confusion matrix and see how many mistakes am I making and where are they being made. I can also go and look at the Roc Curve, and this is based on different species, but we see Setosa and has the area of 1, so it's covering up the whole space, and we don't even see the line. Virginica and versicolor are essentially the same line here, so it's not that interesting of a Roc Curve. So we have a lot of nice functionality in this approach. I can also do discriminant analysis, which is a method I'm very familiar with, and like in discriminant analysis, looks at projecting the data by determining what will minimize the class boundaries within the class boundaries and maximize the distance between the classes. It's very similar conceptually to principal components of factor analysis, which are doing more of eigenvector projection based on covariance matrices. So it's different projections, but I get similar looking results between the two. And I instantly I can highlight what points are in what regions. So I know the reds are all Setosa. That's not that exciting. But I can look and see where is discriminant analysis making mistakes, and it's probably in this region. So I can just highlight the observations I care about, go back to the data table, and see where what observations are the ones between the class boundaries. I can also look at the scores, the projections, the all discriminant scores is minimized, so we don't have to see this giant table. We can also go and look at the covariance within group covariances or the correlations. And we can start to see what, based on what method did discriminant analysis make its decisions. I can look at the groupings, get summaries, statistics. I can look at the confusion matrix, and we can look at a lot of other details, including all sorts of statistical tests. So there's lots of things at our disposal. We can open up the the same within matrix we saw below. So there's a lot of stuff at our disposal here. JMP just provides us almost everything we would want. It's just finding what we need and where to get it is usually the difficulty. So let's close this one. We've covered some basic data wrangling. a little bit about dimensionality reduction. So if I go and revisit my principal components, I can dig into a type of dimensionality reduction here. I can first look at my spree plot, which has my eigenvalue score for each of my principal component loadings, the percent of variance explained, and by a basic Pareto rule, we might want to go down. We might want to select components that explain 80 or 90% of the variability. Or we might use a rule like Kaiser that says one eigenvalue above 1 or above the mean eigenvalue. So if we take the first approach, what we want to do is select the first two principal components, component 1 and 2, which explain about 92% of the variability. And we see a nice Pareto chart in this table. I can go and look at, if I click the little red triangle, all sorts of options here. And the loadings matrix is what we usually care about in principal components to reduce dimensionality. And this is how's each principal component, which is I compute the covariance matrix of the data, take the eigenvalues, eigenvectors of that covariance matrix, and then project the data based on those eigenvectors. The loadings matrix gives me an understanding of how correlated are the original data variables to these components, and now I can go and interpret what I'm seeing. And we see principal component 1 is correlated about 90% with the sepal length, negatively with sepal width, and almost perfectly with petal length and petal width. So this is very much a petal component with some sepal length information, while principal component 2 is almost entirely containing the sepal width data. So now we can have some interpretation of this. We look further out, principal component 3 and 4. We don't see anything loaded heavily there, but it's going to get progressively lower as we go on, especially if we've seen higher numbers earlier. And we see a general projection in what direction are things going in. We can also select what we want to view things as. So I'm viewing component 1 and component 2 by default. These explain most of the variation, so those are the logical first ones to view, but there might be some information in lower and higher order ones. So if I click component 1 versus component 3, or component 2 versus component 3, now we see that there's really no understanding of the data. It's just a random blob. Or component 2 versus 4, or 3 versus 4. We can see, is there anything else we want to understand in this problem? And there doesn't appear to be here, but this is a small data problem, so that makes sense. We can look at all sorts of other things in here, including we can save our principal components. I hit save. It asks me how many I want to save. I probably want to save 2. And now it's giving me the principal components score value for the observations, and if I can go take that further. So if I wanted to go and put that into another method to analyze, maybe classify based on principal components, which have already reduced the dimensionality of the data, now I have that available. This doesn't take too long to code if I had to code it, but it's nicer if I can just get that from a drop-down menu. Now, one thing I briefly mentioned was the Pareto Rule, and another data set that you can download from my books available data is called the West Virginia Pareto Data. This is from a West Virginia Medical Journal issue from a few years back, looking at retirement homes and rehab facilities in West Virginia and the type of injuries. And it's organized from the most numerous type of injury to the least. But if we were running the facility, trying to make management decisions on what corrective actions do we need to to work in our facility, let's assume these are things we have some chance of correcting. We need to know what to focus on. We see that femur fracture is the most common injury. Intracranial hemorrhage is the next common, and these are almost all associated with falls. Is there something we should focus on? So if we want to go select analyze, we can plot this with a Pareto plot. So a Pareto plot is just a histogram that's organized from highest to lowest in occurrence. And I select Pareto plot. I want calls. So this is the problem I'm trying to focus on. And the number with injury, this is going to be my frequency. So remember I mentioned frequency can be very useful if I'm looking at a tabulated data set, and this is that type of problem. I'm going to put that in frequency. Okay, and now we see that JMP has provided a rather nice visualization. I can drag and drop the size so we can start to see it more. And we see here's the cumulative percentage of occurrence. Here's the total number of injuries. And we have the organization on the diagnosis from highest to lowest. And we have this curve that's gradually reaching 100. So if we were doing a typical business quality control Pareto analysis, we might find the 80% based on the Pareto principle and focus on just those top 80%. So something like rib fracture, lower leg STI, concussion, pelvis fracture, upper arm, lower leg, forearm, head and neck STI, and a femur, intracranial hemorrhage and femur fracture. And now go back and say these are the things we want to focus on. We can also just focus on femur fracture since this is by far the most numerous problem we have. So we have a nice visual way of saying foot STI foot fracture, those might be very bad. Although I've had a foot fracture, it's not the worst thing that can happen to you. But these are not major concerns that we get all the time. We need to focus our energy and our resources to the most numerous problem and try to work at those places. And I think this is the second to last chapter of my book. I was focusing on problems like quality control and areas like that. So I fabricated a data set called medical errors, which you can find in my book and on my webpage. What this has is a imaginary hospital where we have months from January 2015 to December 2016, the number of medical errors per month, and the number of patients seen. And the reason we have both of these numbers is that, as in the case where we looked at the whole U.S., the raw number may not be as important. If I made 10 medical errors and I only saw 10 patients, that's a lot worse than having 10 medical errors and seeing 1,000 patients. And we can visualize how bad are we or good are we relatively per month by, once again, going to a quality and process problem. And what we really want to look at is a control chart. So a control chart has a sequence approach to examining what type of data problems do you have. So we have a lot of options here, from a run to an X bar. X bar is the easiest to interpret. X bar is just a mean. So if I take five patients out of the hospital out of a day, I survey them. My mean from that day is out of 5. And so X bar is going to plot the local mean from the 5. And if I do 5 every day, I'd be looking at the mean response over time. We don't have that problem. We have something called a P. So this is a proportional chart. We skipped over IR. IR is just X bar without multiple samples. We have a variety of other options. So P will give us a very basic control chart. So I have medical errors. That's my process. Sample size is my patient seen. So what this will do is what we notice is the second I drop sample size in there, the constant size disappeared. So implicitly, JMP says you probably had 100 samples. That's just a rough number for proportions out of 100. But if I drop in patient size, you'll know I have a moving number of samples. I hit OK. And what we have are really a bunch of local confidence intervals. And we see our values for each day. Now I could have dropped in I forgot to drop in them up. So let's go and redo view analysis. Relaunch analysis is what I want to do. So drop down, relaunch analysis. So patient seen is my sample size. I can do sample label. I can drop in the month, and this will make my legend a lot nicer. Hit OK. And now I have a nicer looking table. And it's always nice to know that I can usually go back and restart my analysis by clicking on relaunch or redo something. And if I really make a lot of changes, I can just redo the analysis and get back to the initial screen. And we have proportion of medical errors on our y-axis in our plot. We have the month, and we have upper UCL and LCL. These are upper and lower control limits. And what these are really doing is giving me a confidence interval around each month's values. So it's doing essentially a proportional confidence interval. It gives us the average across all of the months, and it will show us at what point do we stay within bounds or do we move up or out. And we see we have one point where we seem to have received a lot more errors than we expected based on the general trend, and that's June of 15. And so now we've been able to find in all this data what observations may or may not show a problem in our process. We could follow other heuristic rules to say, is our process in control, out of control? But that's something for another day. And you know, this is a relatively straightforward way of using that. And that gets into our last option. And we've talked about this throughout in all of our problems. Is we have a lot to analyze and interpret. So we've done an analysis. We have to interpret and add meaning to this. And as in the last case, the meaning is that something was happening in June of 2016 that we might have wanted to examine. That's statistically anomalous compared to the rest of our data. Now, ideally, we want to start with a hypothesis to test. So that's where you're doing your R1, and you say I'm collecting this amount of data to study this general hypothesis. But sometimes there's just a general, I have data I want to examine. So Fisher Iris is one example. Fisher developed Scrimmage analysis using this Iris data set as an example, so we know that fits into the problem. But there's a lot of other methods we can explore with that and try to provide meaning to the data. There's also a need to link our subject matter expertise, our knowledge from theories, and our results from JMP. So I know a little bit more about iris flowers after studying this data set for a long time. But when we start talking about BDNF, alleles, wild type, and mutant type, I relied on my colleague to understand the mechanics, and we analyzed and interpreted the data together. So that, I think we'll take questions now, Ruth, because we have about 13 minutes based on my computer.
Super, Trevor. Yeah, thank you so much. We've had a couple questions come in already, and if anyone else has questions, type them in the Q&A or the chat, and I will pass them on to Trevor. So one question that we had early on was, where can you find diagnostics to test if the data fit the assumptions? So as you were exploring things in Graph Builder, someone was asking about this, and then a follow-up question about what if you wanted to consider a non-parametric option for something like ANOVA.
Okay, so those options are built in. So I actually was going to talk about regression diagnostics and chose not to. So if those are those the only two questions we have?
We've got some more coming in.
Okay, so I can briefly, let me go back to an example I was going to show but did not. So I'm going to go back to sample data, and I'm going to open up regression and select ANSCOM. The ANSCOM data is a quartet of regression of fabricated data sets that give us the same regression models. I'm going to give us two examples here. So I'm going to do X1 and Y1. I'm going to do X2 and Y2. And they look very different, but if I do fit mean and fit mean, oh, sorry, not fit mean, fit line, and fit line, I've created I'll remove the fit means. I have the exact same regression model. So I have a linear fit of 3 plus 0.5 times x1 in both cases. My R squares are identical. My ANOVA tables are also identical, as are the parameter estimates and the p-values. Now you can look at this and say, well, that's preposterous, and the other two examples are even more preposterous. You know, the first one looks fairly reasonable, the second one does not look reasonable, but this is just, you know, manipulating the data and saying, well, I know regression is trying to look at the difference from the mean line, so I'll put the mean back in from each point. So it's looking at the distance from each point to the mean, the distance of each point to the line, distance of the line to the mean, and that's essentially everything it's using are quantities from that dimension to compute these parameters of sums of squares, and from that R squared. So how can I find the problem? So this is a simple case, and we can visualize that. But if I go to this little the triangle under fit mean, I can save predicted and residuals. So I'll save predicted, save residuals, save predicted, and save residuals. And we'll have to remember which one is which. And I can examine these. If I had a more complex problem, you can't visualize that and know that our method is preposterous. So let's create two other things. I'm going to create a new column. I'm going to call this standard deviation residuals. So I'm going to standardize residuals 1 and standardize residuals 2. Because this will give me a way to also look for other issues in the models. And this is a formula where all I'm going to do is go and take my residuals. So this is residuals 1, residuals 1 y1 divided by, so I find the divide button, square root of my mean squared error, and it's the same in both cases, 1.53, so that's easy to remember. Hit OK. And all I'm doing is standardize my residuals to get rid of the units, to make it unitless, and I can look for outliers while also looking at the diagnostics of these residuals. Y2 divided by 1.53. So basic diagnostics for regression ANOVA would be linearity. So we'll stay with our original ones, our original residuals. I have my distributions of residuals. I can do a normal quantile plot to try to find, you know, does the, and Windows 10 is being my friend again, to try to find, does the shape of the residuals deviate from the assumption. So the general assumption would be for a normal quantile plot, they would follow this trend line, and that would be the ideal case. If I see a shape or points outside this confidence interval, they would not be violating an assumption. This is better than relying on the histogram, which especially in small sample sizes can fool you, and it's about as reliable as using an exact test. So, and we can see on for the first model Y1, we more or less have a linear trend. So these are the normal quantiles at the bottom. Here's the z-scores for the observations at the top. And all this does is resort the data, look at how many samples we have, what z-score do I get for my numbers and the distribution. But for the second model, we see a curving trend. We see a lot more points up in this range, and we start to see a decrease. So we can sort of catch the problem here at this moment where we look at the residual normalities. We don't have to stop there. Let's go back to our data table and go back to Graph Builder. So with Graph Builder, what I want to do is I'm going to go and put our I saved the wrong thing there. I put our Y1, so instead of predicted, I'll put the real data just to save time. And I'll put the residuals on the Y-axis. Residuals. And let me go back and save the predicted. Save predicted. So I'm going to put predicted Y1 and residuals Y1. That looks a little odd. Let me just save the wrong one in a hurry. Now save those one more time. Yeah, that looks more appropriate. I'm going to unclick this, highlighted area because that's a default setting. So for predicted by residuals, I see a random scatter for the first case. Switch that to residuals Y2 by predicted Y2. I see a curve here. So the first case, I'm catching, the non-linearity in the residuals. But here, when I look at residuals by predicted, I already see that they violate the assumption. If we go back to another assumption, we don't have this normality. We also have independence, and we see a non-independence here between the residuals. One value pretty much predicts the next, whereas for the first case, the model that looked appropriate, we see a random scattering. It's almost like a shotgun hit the screen. Now I will go back, and I don't trust the formula I put in here, but what I'm going to do is just change Y1 to the residual Y1 that I know is good. And I'm going to change this to here. And I'll put the residual Y2 that I know is good. And I'm going to drag over the standardized residuals. So I have Y1 and standardized residuals. And we notice the shape doesn't change, but the axis we're on changes. Now the axis on the Y-axis is still from -2 to 2, so the points look like they shift down, but it's about the same approach. And the nice thing about this is I can look for outliers. Now I can view the Y-axis as in units of standard deviation and look for how many points are we away, and I can use a heuristic rule based on a normal distribution. How many points would I expect to see at this many standard deviations? Residual 2 versus predicted 2. I don't have any outliers, so I still have the shape. So Ruth, I hope that answered that question.
Yeah, that was really helpful, Trevor. Thanks for showing the exploring residuals, because I think everyone who's doing any analysis needs to know how you do this. We all need, this is a pretty important part of modeling well statistically. We had a couple other questions. So I'm really excited about the questions we got. We got much deeper questions than we usually do. So a lot of people asking very specific questions. Someone asking about documentation for how calculations are done in JMP, like the F value in ANOVA or the formula for cross-validation of PCA.
So you have to dig into, there's a lot of documentation on FAST's webpage. And just about every equation, especially like F ratio, you can find, at some point in a FAST document. They're all freely available. They're all PDFs you can download. I've never found an equation that I had a question about that I could not find and it's documented.
Yeah, and I would follow that up with under the help menu in JMP, we have a lot of documentation and links to documentation directly from the help menu. So in the help, there's a searchable help.
The help.
Yeah, right at the top, the JMP help option right under. Yeah, that will take you to a searchable help online, or I think. Well, okay, maybe it's in the files in your. Yeah, built in.
My Firefox is going to explode if I.
Yeah, no problem. Yeah, so there are lots of resources, we hope. If you ever are stuck, if you're a new JMP user or an old JMP user and you just want to figure out details about a certain procedure and you can't find the answer, our JMP support is also really helpful. And so you can email them directly at support@jmp.com.